Not even light can escape the event horizon. This boundary around a black hole is the universe's ultimate point of no return. By the end of this journey, you will understand the startling possibilities for what happens beyond that edge, from the shattering of physics to gateways to other realities. We will investigate if everything that falls in is truly lost forever, and what strange new laws might govern the interior. What does it truly mean to cross a line from which there is no coming back? This invisible sphere marks the final border where the universe's rules, as we know them, cease to apply. Think of it as the edge of a cosmic waterfall. For a long time, a river flows smoothly, and a boat can still paddle away. But once it crosses that precipice, the current becomes irresistible, and the plunge is absolute. The event horizon is that point of no return for spacetime itself. It is not a solid surface you could bump into, but a one-way membrane in the fabric of reality. Nothing that passes through, not even a single particle of light, can ever send back a signal. The size of this boundary is known as the Schwarzschild radius, a distance determined solely by the black hole's mass. A more massive black hole has a larger, more spacious event horizon. This profound idea emerged directly from Einstein's theory of general relativity, which describes gravity as the warping of space and time. Just months after Einstein published his equations, the physicist Carl Schwarzschild found a solution that described this very phenomenon, a point where the mathematics indicated a boundary of infinite curvature. Crossing this threshold is a one-way trip, a step through a door that immediately locks shut behind you. It is the gateway from the known universe into a realm of pure mystery, and our journey is only just beginning. The universe's ultimate trap is woven from the very fabric of reality itself. To truly grasp the power of a black hole, we must first understand gravity not as a simple force, but as the curvature of spacetime. Picture a taut rubber sheet, smooth and flat. Place a heavy bowling ball in its center, and the sheet stretches downward, forming a deep well. A marble rolled nearby will spiral inward, not because of a mysterious pull, but because it is following the curved path created by the heavier object. This is the essence of Einstein's revelation. Massive objects like stars and planets warp the four-dimensional fabric of the cosmos, and what we feel as gravity is simply matter following these curves. A black hole is what happens when an unimaginable amount of mass is compressed into an infinitesimally small point, creating a pit in spacetime so deep and so steep that nothing can climb out. The mathematics of Einstein's field equations show us that when matter is squeezed beyond a critical density, spacetime curves toward a breaking point, predicting the formation of a gravitational singularity. At the event horizon, this curvature becomes infinite. All possible paths, every direction an object could try to travel, point relentlessly inward. This is why light itself cannot escape. It is not being pulled, it is simply following the only road available, a one-way street into the abyss. This extreme warping also twists time in a phenomenon called gravitational time dilation. For an outside observer watching an object fall toward a black hole, its clock would appear to tick slower and slower. As the object approaches the event horizon, its time seems to stretch into a frozen moment, forever poised at the brink. For the object itself, however, time flows normally as it crosses the threshold without a jolt. This bizarre divergence is a direct consequence of spacetime being stretched to its absolute limit. With spacetime so profoundly broken at the edge, what monstrous reality awaits within the darkness? For the astronaut falling toward this cosmic waterfall, the final approach is a silent, terrifying ballet of physics. From their own perspective, crossing the event horizon is an uneventful transition, a moment passing without a shudder or a flash of light. Yet their view of the universe outside is undergoing a profound and irreversible transformation. Every star, every galaxy behind them begins to shift. Their light, struggling against the immense gravity, stretches into longer, redder wavelengths, dimming and shifting toward the invisible. The entire cosmos seems to crowd into a shrinking, brilliant disk directly above them, a final pinhole of light that then winks out into absolute blackness. They are now cut off, sailing into a darkness from which no signal can ever return. Meanwhile, to a friend watching from a safe distance with a powerful telescope, a different and equally bizarre scene unfolds. The astronaut appears to slow down, their motion grinding to a halt as they near the invisible boundary. Their image reddens and fades not in a flash, but over an unimaginably long stretch of time, until they are frozen like a ghostly photograph, eternally poised at the edge. This is the stark paradox of the event horizon, two realities existing simultaneously. But for the astronaut, the physical reality is brutally immediate. The difference in gravitational pull between their head and their feet becomes monstrous. If they were falling feet first toward a stellar mass black hole, the force on their feet would be vastly stronger than the force on their head. They would be stretched, elongated into a stream of atoms in a grisly process physicists call spaghettification, torn apart by tidal forces long before reaching the central singularity. Some theoretical physicists propose an even more violent end. The firewall paradox suggests that the event horizon might not be a smooth gateway at all, but a searing wall of high-energy radiation. According to this contentious idea, the vacuum of space itself might transform at the boundary into an inferno, instantly incinerating any matter that dares to cross. This remains a deep puzzle, a sign that our understanding of physics is incomplete. The crossing is a violent, transformative threshold, a shredding of both form and information. But what lies beyond this chaotic entryway? Does the turmoil simply end, giving way to an even stranger calm? Beyond that violent entryway lies the ultimate mystery, the singularity itself. This is the black hole's dark heart, a point where all concepts of space and time are shattered. General relativity gives us a clear yet terrifying prediction. All the matter that ever crossed the event horizon, every star, every planet, every astronaut, is crushed into an infinitely small point of infinite density. The very fabric of spacetime which weaves the universe together is torn apart. The orderly rules of physics that govern our reality simply cease to function here. How can we even comprehend a place where space has no volume and time has no forward direction? The mathematics of Einstein's theory points to this inevitable conclusion, but it also signals its own limitations. It screams that a new set of laws must take over. For decades, physicists Roger Penrose and Stephen Hawking used powerful mathematical theorems to prove that, under the extreme conditions within a black hole, the formation of a singularity is unavoidable. Their work showed that the path of any object falling inward must ultimately end at this point of infinite curvature. Yet this very infinity is a clue that we are missing a crucial piece of the puzzle. At such incomprehensibly small scales, the wild rules of quantum mechanics must become the dominant force. General relativity describes the gravity of the large, while quantum mechanics governs the chaos of the very small. The singularity is where these two titanic theories meet and collapse into contradiction. So what truly resides at the center? Is it a perfect, structureless point as classical physics suggests? Or could it be something else entirely? A dense, exotic object with a complex and unknown structure that our current science cannot yet describe. Unlocking the nature of the singularity is not just about understanding black holes. It is about finding the key that will finally unite our two greatest descriptions of reality, revealing a new, deeper truth about the universe itself. This paradox strikes at the very heart of physics, forcing us to question if anything in the universe is truly permanent. According to the unbreakable rules of quantum mechanics, information can never be destroyed. It can be scrambled, transformed, or hidden, but never erased from existence. Think of burning a book, the pages turn to ash and smoke, seemingly gone forever. Yet, in principle, if you could track every single particle of ash and wisp of gas, you could theoretically reconstruct the entire book, every word and every comma. The information is merely transformed, not lost. A black hole, however, presents a terrifying exception. When an object falls in, every bit of information about it, what it was made of, its shape, its history, seems to vanish from our universe, trapped behind the event horizon. The problem deepens with Stephen Hawking's stunning discovery that black holes are not entirely black. They slowly evaporate over astronomical timescales, emitting a faint whisper of energy now known as Hawking radiation. This radiation, Hawking argued, is entirely random and thermal. It carries no information about what fell in. So when the black hole finally evaporates and vanishes, what happens to all that information? It appears to be permanently erased, a direct violation of quantum law. This is the black hole information paradox. The physicist Leonard Susskind passionately argued against this idea, engaging in a famous scientific debate with Hawking. Susskind maintained that information must be preserved, that the universe does not forget. His work helped lead to a radical proposal, the Holographic Principle. This mind-bending idea suggests that all the information about everything that falls into a black hole is not lost inside, but is instead perfectly encoded on the two-dimensional surface of its event horizon, like a cosmic fingerprint smeared across a sphere. The three-dimensional interior we imagine is, in fact, a holographic projection of that data. Another possibility is that evaporation stops at the last moment, leaving behind an infinitesimally small, information-packed remnant. This paradox is far from settled. It forces physicists to confront the deepest questions about the nature of reality, space, and time. If information is not lost, then where does it go, and how does it escape a region from which nothing should return? But what if the singularity is not the end of the story? A third, breathtaking mystery suggests that some black holes might not be tombs at all, but tunnels. The equations of general relativity themselves hold a tantalizing possibility, a theoretical shortcut through space-time known as a wormhole. Picture the event horizon not as a one-way street to destruction, but as the entrance to a cosmic subway system. Instead of being crushed at the center, you would find yourself rushing through a smooth, geometric throat, a tunnel connecting two distant points in the universe, or perhaps even bridging two separate realities. You could step into a black hole here and emerge an instant later in a galaxy millions of light years away, or in a universe with entirely different physical laws. This is not pure fantasy. The mathematics first developed by Albert Einstein and Nathan Rosen described such bridges, often called Einstein-Rosen bridges, as possible solutions to the equations of gravity. For decades, however, these structures were seen as mathematical curiosities, unstable pathways that would snap shut the instant anything tried to pass through. The tunnel would collapse into a singularity faster than light could travel through it. Then came the work of visionary physicists like Kip Thorne. He and his colleagues investigated whether a wormhole could ever be made traversable, held open long enough for a ship or even information to pass through. They found a potential, though fantastical, key exotic matter. This is not simply strange matter, but a theoretical substance that possesses negative energy density. It would push the fabric of spacetime outward, acting as a kind of anti-gravity to prop the wormhole's throat open against its own immense gravitational pull. While we have observed tiny, quantum-scale effects that hint at negative energy, creating or finding enough of this exotic matter to stabilize a macroscopic wormhole remains far beyond our capabilities. The implications of such a discovery would rewrite our cosmic map. Wormholes could serve as the ultimate shortcut, rendering interstellar travel possible not by moving fast but by folding space itself. They could, in theory, become time machines, creating closed loops in time that challenge our very understanding of cause and effect. This thrilling possibility transforms the black hole from a monstrous consumer into a potential cosmic connector, a gateway hiding in the most terrifying of places. It offers a profound alternative to the grim fate of the singularity, suggesting that beyond the point of no return might lie not an end, but a beginning somewhere else entirely. The singularity's infinite density is a mathematical cry for help, a sign that our current physics has reached its breaking point. To truly understand what lies within a black hole, we must journey deeper into the unknown, to a realm where the very concepts of space and time dissolve. This quest leads us to the most profound frontier in modern physics, the search for a theory of quantum gravity. Its goal is to stitch together the cosmic rules of general relativity with the chaotic, probabilistic laws of quantum mechanics. Without this unified theory, the black hole's core remains an impenetrable mystery. At the heart of this puzzle is the Planck scale, an unimaginably tiny domain where the smooth, continuous spacetime we know is believed to break down into a seething, chaotic foam. Picture an ocean's surface on a calm day, a vast and gentle expanse. Now zoom into the molecular level, where water is a frenzied dance of particles constantly appearing and disappearing. Spacetime at this fundamental level may be just as turbulent, with tiny bubbles of geometry fluctuating in and out of existence. In this roiling quantum foam, the notion of a perfectly smooth, infinitely dense point may be impossible. The violent gravitational collapse that forms a singularity in classical physics could be tamed by these wild quantum fluctuations, preventing the infinite breakdown and offering a stable structure at the very center. Two leading paths guide this search, each with a unique vision of reality's bedrock. String theory proposes that the fundamental constituents of the universe are not point-like particles, but incredibly tiny, vibrating loops of energy. An electron is not a dot, but a specific harmonic vibration of a string. A photon is another note in this cosmic symphony. Within a black hole, these strings could interact in ways that prevent the formation of a true singularity, instead creating a dense, hot ball of vibrating strings often called a fuzzball. Another approach, loop quantum gravity, takes a different route. It suggests that space and time themselves are not smooth and continuous, but are woven from a network of finite, quantized loops. Think of the fabric of reality as a tapestry made of individual threads. There is a smallest possible stitch, a tiny unit of space, meaning you cannot divide a volume infinitely. This theory directly challenges the singularity, proposing that the immense gravitational crush inside a black hole hits a quantum wall. Instead of collapsing to nothing, the matter could rebound in a cosmic bounce, spewing its contents out into a new region of spacetime. Theoretical physicist Carlo Rovelli is a leading voice in this field, suggesting that a black hole might not be a final destination, but a transformative gateway. In this view, crossing the event horizon and approaching the core does not lead to annihilation. The quantum bounce would be so powerful that it effectively turns the black hole's interior into a bridge, a portal to another universe or a distant part of our own. The black hole would be a one-way door to a new cosmic neighborhood. This is not the fragile, collapsing wormhole of classical relativity, but a robust transition enforced by the quantum nature of gravity itself. The journey to find this ultimate theory is more than an academic exercise. It is the key that will finally unlock the secrets beyond the event horizon, revealing whether the point of no return is truly an end or merely the start of a far grander voyage. The darkness at a black hole's heart might not be a final destination, but a cosmic revolving door. This leads us to a fifth profound mystery, the existence of white holes. If a black hole is a one-way drain, a white hole is its theoretical opposite, a gushing fountain from which matter and energy erupt but can never enter. Picture the entire life cycle of a black hole reversed, a celestial geyser spewing out everything it once consumed. The mathematics of general relativity allows for this stunning symmetry, treating black holes and white holes as two sides of the same coin. In this view, the event horizon we fear could simply be the entrance to a bridge, with a white hole's horizon serving as the exit into a new region of space-time. You could not travel back through the white hole, just as you cannot escape the black one, but the journey through the tunnel would connect two separate realities. This concept finds powerful support in some models of quantum gravity, particularly those that seek to eliminate the problematic singularity. The theory of loop quantum gravity, for instance, suggests that the immense gravitational collapse inside a black hole does not end in an infinitely dense point. Instead, the crushing pressure triggers a quantum rebound, a big bounce. The collapse reverses into an explosion, transforming the black hole into a white hole. This would not happen quickly, at least not from our perspective. For an outside observer, the transformation of a stellar black hole might take billions of years, but for anything that fell inside, the bounce could be nearly instantaneous. So why have we never observed a white hole? If they exist, they are likely incredibly unstable or transient. A white hole would be a violent, short-lived event, perhaps flashing into existence for a mere moment before the geometry of spacetime around it collapses. Another compelling possibility is that they do not exist in our universe at all. The white hole end of the tunnel might reside in an entirely different universe, or in a distant part of our own cosmic history. This idea sparks a breathtaking question about our own origins. Could our entire universe, with its vast expansion and primordial energy, be the result of a white hole eruption from a black hole in a parent cosmos? In this speculative scenario, the Big Bang was not a singular creation from nothing, but a great rebound from a collapsed region in a pre-existing reality. Each black hole in our universe could then be a seed for a new cosmos, a transformative gateway in an endless multiverse. This mystery completely reframes our understanding, suggesting that beyond the point of no return lies not oblivion, but the potential for rebirth on a scale beyond comprehension. The idea of a dark star was born not in the flash of modern telescopes, but in the quiet calculations of an 18th-century clergyman named John Michell. Pondering Newton's laws of gravity and light, Michell reasoned that if a star were sufficiently massive and dense, its gravitational pull would be so immense that not even light could escape. He called these objects dark stars, a brilliant, speculative leap that lay dormant for over a century, a concept waiting for a theory powerful enough to bring it to life. That theory arrived with Albert Einstein's general relativity in 1915, which redefined gravity as the curvature of spacetime. Just a year later, Carl Schwarzschild found a solution to Einstein's equations that described this very phenomenon, a point of infinite curvature, though its true meaning as a physical boundary was not yet fully grasped. Einstein himself was deeply skeptical, believing that nature would find a way to prevent such bizarre objects from actually forming. The debate intensified with a young physicist named Subrahmanyan Chandrasekhar. On a long sea voyage from India to England, he performed calculations showing that a dying star above a certain mass limit, now known as the Chandrasekhar limit, could not support itself against its own gravity. It would collapse endlessly. The established scientific community, led by the eminent Sir Arthur Eddington, publicly ridiculed the idea, with Eddington arguing that a star would surely find a way to avoid such a fate. Yet Chandrasekhar was correct. This work paved the way for understanding that massive stars could indeed collapse into what we now call black holes, a term famously popularized by the charismatic physicist John Archibald Wheeler. It was Wheeler who gave these objects their unforgettable and ominous name, cementing their image in the public imagination. But perhaps the most revolutionary insights came from Stephen Hawking. Working with Roger Penrose, he used powerful mathematics to prove that singularities were not just mathematical quirks, but inevitable outcomes of gravitational collapse. Then, in a stunning move, Hawking turned the concept on its head. By applying quantum theory to the edge of a black hole, he showed they are not perfectly black. They slowly leak a faint glow of radiation, now known as Hawking radiation, and can eventually evaporate entirely. This discovery created the Great Information Paradox, a puzzle that continues to drive theoretical physics today. This entire journey, from Mitchell's dark stars to Hawking's evaporating black holes, shows how our understanding has been forged through bold ideas, fierce debates, and the relentless pursuit of truth. We have come so far, yet every answer has revealed a deeper, more fascinating question about the nature of reality itself. Our understanding of these cosmic monsters is built not by staring into the void, but by observing the violent chaos they create at their edges. Since black holes themselves are invisible, astronomers act as cosmic detectives, piecing together clues from the intense environment just outside the event horizon. One of the most telling signs is the accretion disk, a swirling, superheated maelstrom of gas and dust spiraling inward at near light speed. As this material is torn apart by immense tidal forces, it heats to millions of degrees, glowing fiercely across the entire electromagnetic spectrum before it vanishes. We see this brilliant, doomed halo around the supermassive black hole at the center of our own Milky Way, a beacon pointing directly to the darkness within. But the most definitive evidence arrived in April 2019, when the Event Horizon Telescope collaboration unveiled a landmark image. This was not a picture of the black hole itself, but of its shadow, a dark silhouette cast against the glowing accretion disk of the giant galaxy M87. This stunning achievement, the result of synchronizing radio telescopes across the globe to create an Earth-sized virtual dish, gave humanity its first direct visual proof of an event horizon's existence. Shepard Doleman, the project's founding director, called it a remarkable validation of Einstein's theory and a new window into these extreme objects. Another revolutionary way we listen to black holes is through the ripples they create in spacetime. The LIGO and Virgo observatories have detected gravitational waves, faint shudders in the fabric of the cosmos caused by cataclysmic events like two black holes merging into one. These signals allow us to hear the final moments of a dance that began millions of years ago, providing precise measurements of black hole masses and spins. As physicist and Nobel laureate Barry Barish noted, this new astronomy allows us to observe the universe in a completely different way, revealing phenomena that were once entirely hidden. Every X-ray flare from a shredded star, every wobble in the orbit of a nearby star, and every gravitational wave chirp is a piece of the puzzle. These observations from the very edge fuel our deepest curiosity, providing the data that theorists need to push further, to dare to ask what truly lies beyond that point of no return. These digital laboratories are where our theories face their ultimate test. Inside the world's most powerful supercomputers, equations spring to life, creating virtual black holes that allow us to explore their secrets without ever crossing the event horizon ourselves. Teams of researchers, like those at the Perimeter Institute for Theoretical Physics, feed the complex laws of general relativity and quantum mechanics into these machines. The computers then calculate, step by minuscule step, how spacetime warps, twists, and ultimately breaks under such extreme gravity. We can watch as a simulated star is torn apart, its gas forming a brilliant, swirling accretion disk before vanishing into the darkness. One of the most fascinating structures revealed by these simulations is the ergosphere. This is a region just outside the event horizon of a rotating black hole where spacetime itself is dragged into a whirling vortex. Nothing can stand still here. The fabric of reality is moving so fast that it pulls everything along with it, like a powerful cosmic current. The simulations show that it is theoretically possible to enter the ergosphere and escape, but only if you are moving faster than the speed of light relative to this dragged space. Since that is impossible for matter, the ergosphere acts as a cosmic carousel, imparting immense energy to anything caught in its flow. These virtual experiments also trace the paths of countless light rays, showing us how their trajectories are bent into wild loops and corkscrews by the intense gravity. We can see the black hole's shadow form, not as a simple circle, but as a complex dark patch ringed by a brilliant, warped halo of light, a prediction that was stunningly confirmed by the Event Horizon Telescope's real-world image. By tweaking the parameters, scientists can ask profound questions. What happens if we inject quantum information into the simulation? Does it get lost forever at the singularity? Or is it somehow preserved on the event horizon, as the holographic principle suggests? These are not just abstract puzzles. Every simulation is a bridge, spanning the vast gap between what our telescopes can see from the safety of the outside and the terrifying, unseen physics governing the interior. They allow us to run experiments that are impossible in the real universe, testing the limits of our knowledge and daring to visualize the truly unimaginable. These cosmic predators come in several distinct varieties, each born from a different kind of violence. The most common type is the stellar mass black hole, the ghost of a giant star. Picture a star many times more massive than our Sun. For millions of years, it burns through its nuclear fuel, a constant battle between the outward push of fusion and the inward crush of gravity. When that fuel finally runs out, the battle ends in a catastrophic instant. Gravity wins. The star's core collapses, triggering a titanic supernova explosion that blasts its outer layers into space. What remains is a crushed core, an object so dense that it crosses the threshold and vanishes behind an event horizon. This is the birth of a stellar mass black hole, typically weighing between a few to several dozen times the mass of our Sun. We have confirmed their existence by watching their gravitational influence, like the first one ever discovered, Cygnus X1, which orbits a companion star and voraciously pulls gas from it, heating the material until it glows with intense X-rays. Then there are the true monsters, the supermassive black holes. These behemoths, millions or even billions of times the mass of our Sun, lurk at the very heart of nearly every large galaxy, including our own Milky Way, where Sagittarius, a star, holds sway. Their origins are one of the great unsolved puzzles in cosmology. How did they grow so immense, so quickly? One leading theory suggests they started from massive seed black holes in the early universe, perhaps formed from the direct collapse of enormous gas clouds. These seeds then gorged themselves on surrounding gas, dust, and stars, and merged with other black holes over billions of years, growing to their present staggering sizes. But there is a third, more elusive possibility: primordial black holes. These are not born from dying stars, but are thought to be fossils from the universe's first frantic moments. In the extreme density and turbulence just after the Big Bang, pockets of space could have collapsed directly into black holes. Unlike their stellar and supermassive cousins, primordial black holes could be any size, from smaller than an atom to as massive as a planet. A single one with the mass of a mountain could be passing through our solar system right now, completely undetected. The environment you would encounter inside a black hole depends entirely on which type you fall into. Plunging into a stellar mass black hole with its smaller, tighter event horizon would subject you to ferocious tidal forces, spaghettifying you long before you reach the center. A fall into a supermassive black hole with its vast and more gentle gravitational gradient might be a much smoother ride across the threshold. This classification is not just a cosmic catalog. It is the key to understanding the different doors that might open at the point of no return and the wildly different journeys that could await within. This bizarre slowing of time is one of relativity's most profound and unsettling predictions. As a clock falls toward the event horizon, its behavior becomes a matter of perspective. For a distant observer watching through a powerful telescope, the clock's ticks would grow further and further apart, its light reddening and dimming until it appears frozen, a ghostly image eternally painted on the threshold. This is the origin of the frozen star illusion, where from the outside nothing ever seems to cross the line. Yet, for the astronaut holding that same clock, nothing strange happens at all. Their watch ticks at its usual rhythm, their heartbeat remains steady, and they cross the event horizon on schedule, noticing no sudden jolt or dramatic change. This radical divergence in experience is governed by a precise mathematical relationship from Einstein's equations. The closer an object gets to a massive body, the more severely space-time is warped, and the slower time flows relative to a distant point. The equation for this gravitational time dilation tells us that time nearly grinds to a halt as one approaches the event horizon. This is why no signal from inside can ever reach the outside universe. Any light pulse or radio transmission sent by the falling astronaut after crossing the boundary would have its frequency stretched to infinity, its energy drained to nothing by the immense gravitational field. It would take an infinite amount of time for that signal to climb out, meaning it never arrives. We can adapt the classic twin paradox to this extreme environment. Imagine one twin remains on a safe space station, while the other bravely journeys toward a black hole. The traveling twin falls closer and closer to the event horizon. From the stationary twin's perspective, the traveler's life processes slow to a crawl. A single minute for the traveler might span years, decades, or even centuries for the sibling watching from afar. By the time the traveler's image freezes at the edge, the sibling might have lived a full lifetime, never witnessing the actual crossing. Yet for the traveler, their own subjective time continues normally until they meet their ultimate fate inside. This is not a mere illusion, it is the actual warping of the cosmic fabric, a fundamental statement about the nature of time itself. It means that the history of the universe, as seen from within a black hole, would appear to rush forward in a blinding flash. Billions of years of cosmic evolution could pass in what feels like a single moment to someone falling inward. This time distortion forces us to abandon any simple idea of a universal now. revealing a cosmos where the flow of time is a deeply personal experience dictated by the curvature of space. A star's final scream is not one of sound but of light. When a wandering star or a cloud of gas is caught by a black hole's gravity, it does not simply vanish in silence. It is torn apart in a spectacular, violent process that illuminates the darkness just outside the event horizon. The material is first stretched and shredded by immense tidal forces, a process called spaghettification for the way it pulls objects into long, thin streams. This cosmic debris does not fall straight in. Instead, it forms a furious, whirling maelstrom known as an accretion disk, orbiting the black hole at nearly the speed of light. Think of a cosmic blender of unimaginable power. The individual pieces of gas and dust collide with tremendous force, creating intense friction that heats the entire disk to millions of degrees. This superheated plasma glows with incredible brilliance, blazing across the electromagnetic spectrum and flooding space with powerful X-rays that our telescopes can detect from millions of light-years away. This radiant fury is the black hole's Last Supper bell, the final conversion of matter into pure energy before it crosses the threshold into darkness. But what becomes of it then, once it passes the point of no return? The journey inward is absolute. According to classical physics, the matter continues its fatal spiral, compressed and pulled relentlessly toward the central singularity. There, the theory tells us, it is crushed into an infinitely small point, its identity and structure erased forever. It adds its mass to the black hole, making it ever so slightly heavier, but all information about what it once was, a star or a planet or a cloud of dust, seems lost. Yet quantum physics offers a startling alternative. The work of physicists Jacob Bekenstein and Stephen Hawking introduced a profound connection between a black hole and thermodynamics. They proposed that the event horizon has entropy, a measure of disorder or hidden information. The more a black hole consumes, the higher its entropy becomes. The Bekenstein-Hawking entropy suggests that the information about everything that falls in is not destroyed at the singularity, but is instead encoded on the two-dimensional surface of the event horizon, pixelated into unimaginably tiny bits. It is as if the horizon acts like a holographic film, storing a perfect scrambled record of all that has been lost within. So is the infalling matter truly annihilated, or is it transformed, its essence preserved as a fossilized imprint on the boundary of the void? This question forces us to confront the ultimate fate of reality itself, probing whether anything in the cosmos is ever truly lost or merely changed into a form we are only beginning to understand. The serene emptiness of space near the event horizon is in fact a seething quantum sea. Stephen Hawking made the startling realization that this quantum activity has a direct and profound consequence for a black hole's destiny. He discovered that black holes are not eternal prisons. They can slowly leak away and vanish. This process hinges on a bizarre quantum quirk, the constant creation and annihilation of virtual particle pairs. Throughout the universe, pairs of particles and their antimatter counterparts flicker into existence for an unimaginably brief moment, borrowing energy from the vacuum before they typically collide and annihilate, paying back the energy loan. But at the very edge of a black hole, the intense gravitational field disrupts this delicate dance. It is possible for one of these virtual particles to be created just on the cusp, with one member of the pair falling inward past the event horizon and the other escaping into the wider universe. The particle that falls in has negative energy, which effectively reduces the black hole's mass. The particle that escapes becomes real, carrying away a tiny bit of the black hole's energy. This is Hawking radiation. It means that every black hole has a temperature, a faint heat glow proportional to its gravity, and is therefore slowly evaporating. For a stellar mass or supermassive black hole, this process is achingly slow, taking far longer than the current age of the universe to make a noticeable dent. But for a tiny, hypothetical primordial black hole, the end could be near. As it evaporates, it shrinks, and as it shrinks, its temperature rises, accelerating the process. The final moments of a small black hole could be a spectacular, violent burst of high-energy radiation and particles, a final flash marking its departure from reality. This incredible discovery, however, created a monumental problem, the information paradox. Hawking initially believed this radiation was purely thermal, a random hiss of heat that carried no information about what had fallen in. If the black hole evaporates completely, all the information about every star, planet, and atom it ever consumed would be permanently erased from the universe, violating a fundamental law of quantum physics. Hawking himself famously declared that this meant information was lost, a position that sparked decades of intense debate. The fate of information falling into a black hole is now one of the most urgent questions in physics. Does it leak out scrambled in the Hawking radiation? Is it preserved on the event horizon as a hologram? Or is it truly destroyed, forcing us to rewrite the most basic rules of our universe? Hawking's radiation did not just give black holes a lifespan, it exposed a deep and thrilling conflict at the frontier of our understanding. This holographic vision of reality turns our intuition inside out. The information that defines everything within a black hole, every atom and every star it has consumed, is not lost in the dark interior. Instead, it is perfectly preserved, painted onto the two-dimensional surface of its event horizon. Think of how a DVD works. The disc itself is just a flat, shiny surface etched with microscopic pits, a two-dimensional code. Yet when you play it, that code projects a rich, three-dimensional world of depth, movement, and sound. The event horizon is that cosmic DVD. The physicist Gerard T. Hooft first proposed this radical notion, suggesting that the universe could be like a hologram, where a lower dimensional boundary contains all the information needed to describe the higher dimensional volume. Leonard Susskind later embraced and expanded this idea, seeing it as the only way to save information from destruction and resolve the paradox that haunted Stephen Hawking. In this view, the black hole's vast, dark interior we imagine, with its crushing singularity at the center, is not the fundamental reality. It is the projection, the illusion. The true reality is the frenetic, encoded data shimmering on the spherical skin of the horizon. This is not just a metaphor. The mathematics of string theory and the laws of black hole thermodynamics both point to this astonishing conclusion. The Bekenstein-Hawking entropy, which measures the hidden information in a black hole, is proportional to the area of its event horizon, not its volume. This is a profound clue. In our everyday world, the information capacity of a space is related to its volume. But for a black hole, the maximum amount of information it can hold is determined by the surface area of its boundary. It is as if the third dimension is an emergent property, a consequence of the complex interactions of data on the two-dimensional surface. So what does this mean for an astronaut falling in? From their perspective, they continue their journey into a three-dimensional space, but from the universe's perspective, they never truly leave. Their information is immediately smeared and encoded across the horizon, their entire history and structure translated into a fantastically complex quantum script. The interior they experience is a seamless, consistent illusion generated by that data, a phantom reality that feels utterly real until the final, crushing moment. This forces a breathtaking question about our own existence. If a black hole's three-dimensional interior is a holographic projection from a two-dimensional surface, could our entire universe be the same? Are the three spatial dimensions we move through, the stars we see, and the planets we walk upon, merely a magnificent hologram projected from a distant, two-dimensional boundary we cannot see? The event horizon is no longer a simple point of no return. It has become the ultimate cosmic hard drive, a library of lost things, challenging everything we assume about the nature of space, time, and reality itself. A black hole could be a cosmic seed, its crushing interior giving rise to an entire new universe. This breathtaking possibility suggests that our own cosmos might not be unique, but one branch in an infinite multiverse, all connected through these gravitational gateways. The singularity, rather than being a final end, could be the very spark of a new beginning, a point of infinite density rebounding in a quantum Big Bang. Our universe, with its galaxies and stars, could be the interior of a black hole born in a parent cosmos, a reality nested within an immeasurable chain of cosmic ancestry. This idea transforms the black hole from a destructive pit into a creative womb. Theoretical physicist Lee Smolin proposed a mechanism for this called cosmological natural selection. In this view, universes that produce more black holes effectively have more offspring. The fundamental constants of physics in these daughter universes might be slightly different, much like random genetic mutations. Universes tuned to be prolific black hole producers would come to dominate the multiverse, explaining why our own cosmos seems so perfectly fine-tuned for forging these objects. It is a compelling story of cosmic evolution, where black holes are the reproductive organs of spacetime. Another visionary perspective comes from Roger Penrose and his conformal cyclic cosmology. He proposes a far grander cycle where the entire universe, after expanding for trillions of years and dissolving into a sea of featureless radiation, can transform itself into the high-energy, Big Bang-like state of a new eon. In this model, the infinitely stretched-out future of one universe becomes the infinitely compressed past of the next. While not solely reliant on black holes, the immense conformal rescaling involved is a similar bridge between cosmic epochs, a death and rebirth on the ultimate scale. But how could a singularity, a point of infinite density, possibly become a new universe? The key likely lies in the unknown laws of quantum gravity. Just as quantum mechanics prevents electrons from crashing into an atom's nucleus, quantum effects at the Planck scale could prevent a true singularity from ever forming. Instead of collapsing to nothing, the infalling matter and energy would hit a quantum wall and bounce, an event of unimaginable power that inflates a new spacetime continuum from the ashes of the old. The black hole's event horizon in the parent universe would then become the point of origin for the Big Bang in the child universe, a one-way door leading not to death but to a new cosmic landscape. This idea offers a profound new role for these enigmatic objects. They are not merely the universe's ultimate trash compactors, but its most prolific recyclers, transforming the end of one story into the beginning of countless others. Every swirling disk of accreting matter, every silent merger in the darkness, could be the midwife to an entire new reality, a universe with its own laws, its own stars, and perhaps its own black holes birthing universes in turn. This profound simplicity is captured by the No-Hair Theorem. A black hole, for all its terrifying power, is an object of startling minimalism. According to classical general relativity, every single black hole in the universe can be completely described by just three numbers: its mass, its electric charge, and its spin, or angular momentum. Everything else is erased. It does not matter if the black hole formed from a star made of hydrogen or iron, or if it swallowed a diamond planet or a cloud of dust. All the unique details, the complexity, the very identity of everything that fell in is permanently lost. The black hole remembers only how heavy it is, whether it is spinning, and if it carries an electric charge. It has no other features, no hair, as physicist John Archibald Wheeler poetically put it. This idea was rigorously developed through the work of scientists like Werner Israel and Brandon Carter, who showed that these three properties are all that remain once the chaotic collapse settles into a stable state. Think of a cosmic blender. You can put in strawberries, bananas, yogurt, and ice. But once the blade has finished its work, the resulting smoothie reveals nothing about the individual ingredients, only their combined volume, color, and consistency. The black hole is that ultimate smoothie, blending the universe into its most basic components. This theorem paints a picture of the event horizon as a perfect eraser, a boundary that scrubs matter clean of its history. It suggests that whatever lies beyond must be equally featureless, a void governed by pure geometry with no intricate internal structure. Yet this elegant conclusion creates a direct conflict with quantum mechanics, which insists that information can never be truly destroyed. This paradox has led to modern investigations into the possibility of quantum hair. Theoreticians like Stephen G. Giddings and others have explored whether subtle quantum fields could imprint a more complex signature on a black hole, a faint fuzz of information that clings to the horizon and preserves a record of what fell in. This quantum hair would be an exception to the classical rule, a way for the black hole to retain a memory without violating the profound simplicity we observe from the outside. The No-Hair Theorem stands as a beautiful and powerful idea, a statement of elegant simplicity that simultaneously points toward the deeper, more complex physics waiting just beneath the surface. A rotating black hole does not simply pull space inward, it twists the very fabric of reality into a vortex. Just beyond the event horizon of a spinning black hole lies a region of pure cosmic dynamism, the ergosphere. This is not a solid surface, but an oblong zone where spacetime itself is dragged into a furious whirlpool by the black hole's immense rotation. Picture a celestial liquid, forced to flow in a circular current so powerful that nothing, not even light, can resist its pull. Within the ergosphere, it is impossible to stand still. The fabric of space is moving faster than the speed of light, and everything caught within it is compelled to move along with the flow. This bizarre phenomenon, known as frame dragging, is a direct prediction of the Kerr solution to Einstein's equations, which describes the unique geometry around a rotating black hole. The paths of light and matter are not just bent here, they are corkscrewed into wild orbits, tracing out the invisible contours of spinning spacetime. This dynamic environment is not just a cosmic curiosity, it is a potential power source of staggering proportions. The physicist Roger Penrose conceived a brilliant mechanism to tap this energy. Imagine an object enters the ergosphere and splits in two. One piece falls into the black hole while the other escapes. Under the right conditions, the infalling piece can be given a negative energy trajectory. And by the law of conservation of energy, the escaping piece must carry away more energy than the original object had. The black hole itself loses a tiny bit of its rotational energy in the process. This is the Penrose process, a way to extract energy directly from a black hole's spin. Astronomers believe this very mechanism, operating on a colossal scale, could be the engine behind the relativistic jets seen erupting from active galactic nuclei. These are beams of matter and energy shooting away at nearly light speed, powered by the rotational fury of a supermassive black hole. By studying the X-rays emitted from the inner edges of accretion disks, scientists can measure the spin of these monsters, observing how the dragging of spacetime influences the light we see. This violent, whirling space just outside the event horizon profoundly shapes the mysteries that lie within. For a rotating black hole, the central singularity is not predicted to be a point, but a ring, a loop of infinite density. The ergosphere is the outer expression of this inner whirl, a preview of the chaotic and twisted geometry that awaits beyond the point of no return. The universe seems to protect us from its own deepest chaos. This is the essence of Roger Penrose's cosmic censorship hypothesis, a bold conjecture that nature abhors a naked singularity. It proposes a fundamental rule that every gravitational singularity born from a realistic collapse must be hidden from our view, permanently cloaked behind the one-way curtain of an event horizon. This is not just a cosmic courtesy, it is a requirement for the very predictability of physics. The equations of general relativity break down completely at a singularity, yielding answers that are not numbers but infinities. In such a place, cause and effect could become untethered, and the future could become fundamentally unknowable. Cosmic censorship acts as a protective veil, ensuring that this lawless region cannot influence the orderly universe outside. Without it, the unpredictable fury of a naked singularity could ripple outward, making the cosmos an erratic and unstable place. Scientists discuss this idea in two forms. The strong cosmic censorship hypothesis suggests that singularities are not just hidden from our view, but that the interior of a black hole is so violently unstable that no observer, not even one falling in, could ever reliably see or measure the singularity itself. It remains a mathematical boundary that cannot be crossed by any meaningful prediction. The weak version simply insists that singularities are hidden from distant observers like us, safe behind an event horizon. But what if this cosmic censorship fails? The terrifying possibility is a naked singularity, a point of infinite density exposed to the rest of the universe. Some mathematical models of rapidly spinning or electrically charged black holes suggest that their inner event horizons might shrink away, potentially revealing the central singularity. If such an object existed, it would be a window into a realm without laws. You could, in theory, send a probe toward it and receive signals back from the edge of infinity. What would it see? The probe might return with answers that are logically inconsistent, or it might report that time itself runs backward in its vicinity. The very fabric of reality would be at risk. This has sparked intense debate among physicists. Could quantum effects, which prevent true infinities in other areas of physics, provide a loophole? Perhaps quantum gravity dresses a naked singularity at the last moment, or maybe the intense radiation from such an object would destroy it before it could form. The question strikes at the core of our quest for knowledge. Are we forever barred from witnessing the universe's most extreme state, or could a crack in this cosmic veil one day appear, offering a glimpse into the true heart of gravity and forcing a revolution in our understanding of everything? The profound connection between gravity and heat was once thought impossible. How could the cold, dark vacuum around a black hole possess something as familiar as temperature? This puzzle led to a revolutionary fusion of ideas, where the laws governing steam engines were found to apply to the universe's most destructive objects. Black holes obey their own version of the four laws of thermodynamics, a cosmic code that reveals their hidden, dynamic nature. The first law is a statement of conservation, linking a change in a black hole's mass to changes in its spin and surface area, much like the first law of thermodynamics links energy, work, and heat. The second law is perhaps the most striking. Just as the total disorder or entropy of an isolated system always increases, the total surface area of all black holes' event horizons can never decrease. When two black holes merge, the area of the new, larger event horizon is always greater than the sum of the two original areas. This cosmic rule ensures that black holes, like messy rooms, only get messier in a way that is permanent and irreversible. It was a young graduate student named Jacob Bekenstein who made the daring leap. He proposed that a black hole's entropy is not just analogous to thermodynamic entropy, it is real entropy, and it is directly proportional to the area of its event horizon. His insight meant that black holes are the ultimate repositories of cosmic disorder, containing an unimaginable amount of hidden information. Initially, Stephen Hawking resisted this idea, arguing that if a black hole had entropy, it must also have a temperature, and therefore it must radiate, which seemed absurd for an object from which nothing escapes. Hawking set out to prove Bekenstein wrong, but in a stunning reversal, his calculations showed that black holes do indeed have a temperature. By applying quantum theory to the space just outside the event horizon, he derived the precise formula for Hawking radiation, confirming that black holes are not static, but slowly evaporating thermodynamic systems. Hawking later admitted that Bekenstein had been correct, a gracious acknowledgement of a transformative idea. This thermodynamic perspective completely reshaped our view. A black hole is no longer a simple, featureless pit. It is a complex object with internal states, a history, and a future. It possesses heat and hides chaos. The physicist John Wheeler, who helped pioneer this field, noted that this connection provides our deepest clue for linking the worlds of gravity and quantum mechanics. The event horizon is not a cold, dead wall, but a warm, dynamic surface thrumming with quantum activity, a frontier where the fate of information and the flow of time are written in the language of thermodynamics. Black holes are not isolated monsters, but deeply woven into the cosmos's greatest enigmas. Their story is inextricably linked to the dark, invisible components that govern the universe, dark matter and dark energy. We cannot understand their full role without confronting these twin shadows. Dark matter, the unseen gravitational glue holding galaxies together, and dark energy, the mysterious force accelerating cosmic expansion, form the backdrop against which every black hole evolves. One of the most compelling speculations is that some dark matter could actually be made of primordial black holes. These ancient relics, forged in the universe's first moments, could be drifting through space unseen, their collective gravity influencing the formation of the very galaxies we see today. If vast numbers of these small, dark holes populate the halos around galaxies, they would provide the extra mass we detect through gravity without emitting any light. This idea remains highly debated, but it illustrates how the search for dark matter leads us directly back to the nature of black holes. At the centers of those galaxies, the supermassive black holes we find are also engaged in a complex dance with dark matter. The incredibly strong gravity at the galactic core is thought to pull in and concentrate dark matter particles, creating a dense spike in the otherwise diffuse halo. This concentrated dark matter could then influence the black hole's own growth, potentially providing an additional source of fuel through annihilations or accretion, subtly shaping its evolution over billions of years. Meanwhile, dark energy casts a long shadow over the ultimate fate of all black holes. As the universe expands at an ever-increasing rate, driven by this repulsive force, the large-scale structure of the cosmos is being pulled apart. Galaxies will become increasingly isolated, and the reservoir of gas needed to feed and grow black holes will eventually vanish. Over timescales so vast they defy comprehension, even the mightiest supermassive black holes will cease to grow, left adrift in an ever-cooling, expanding void. Their final evaporation via Hawking radiation, however, would still lie far beyond even this desolate future. Data from sophisticated computer simulations consistently show that the distribution and behavior of dark matter are crucial for forming the cosmic web where galaxies and their central black holes first coalesce. Observations from telescopes like the Hubble and the James Webb Space Telescope provide the real-world maps that these simulations strive to match, revealing how the invisible hand of dark matter sculpts the visible universe. This broader context transforms our view entirely. A black hole is not merely a cosmic vacuum cleaner or a gravitational trap. It is a dynamic component in a vast, dark ecosystem, its life cycle shaped by forces we are only beginning to perceive. The mysteries of the event horizon and the singularity are not separate from the mysteries of dark matter and dark energy. They are different facets of the same profound puzzle, revealing a universe where the darkness holds the deepest secrets. Science fiction paints the black hole as a shimmering gateway to the stars, a cosmic subway system for intrepid explorers. The film Interstellar gave us a breathtaking vision of this idea, where astronauts plunge into a black hole called Gargantua and navigate a navigable wormhole within its depths, emerging in a distant galaxy. This poetic image is deeply compelling, but how does it hold up against the harsh glare of reality? The physics behind such a portrayal is not pure fantasy. It was guided by renowned theorist Kip Thorne, who used the Kerr metric, a solution to Einstein's equations for a rotating black hole, as the foundation. This mathematics does allow for a theoretical structure known as a ring singularity, a loop rather than a point, which could form the throat of a traversable wormhole. Under these perfect, ideal conditions, the equations suggest you could avoid the crushing singularity and pass through to another place or time. Yet this theoretical possibility is balanced on a knife's edge. The moment you introduce anything real, like a single atom of matter or a whisper of radiation, the beautiful geometry collapses. The wormhole would snap shut instantly, or worse, be filled with lethal radiation and unpredictable chaos long before a ship could even approach. The destructive forces at play are immense. Even if you aimed for a supermassive black hole with gentler tidal forces to avoid spaghettification, you would face the unknown fury of the inner singularity and the blistering energy of the accretion disk. Your ship would be bombarded by X-rays and gamma rays, torn apart by gravitational waves, and potentially vaporized by the very radiation the black hole emits. So, could future technology ever overcome these titanic obstacles? Perhaps a civilization with a mastery over gravity and the ability to generate exotic matter, a substance with negative energy, could theoretically prop a wormhole open. But such concepts live in the realm of distant speculation, far beyond any science we can currently conceive. The chasm between the silver screen dream and the astrophysical reality is vast. Black holes, as we understand them today, are far more likely to be cosmic shredders than cosmic shortcuts. They represent the absolute limits of known physics, a boundary where our imagination soars, but our technology and our very understanding of reality hit a wall. This tension is what makes them so fascinating. They are both a symbol of ultimate destruction and a canvas for our most profound hopes of exploration. To truly wrap your mind around these cosmic enigmas, you can now step into a virtual universe yourself. Interactive simulations and planetarium shows transform the abstract mathematics of general relativity into a breathtaking visual journey. Tools like the Black Hole Hunter app or NASA's own visualization software let you manipulate a digital black hole with your fingertips. You can adjust its mass and spin, then watch in real time as the fabric of spacetime warps around it, bending the paths of starlight into a shimmering corona. These programs calculate the complex gravitational lensing and frame dragging effects, allowing you to see firsthand how a rotating black hole drags space into a vortex within its ergosphere. This is not just an animation, it is a dynamic engine solving Einstein's equations right before your eyes, making the invisible force of gravity something you can literally see and control. For an even deeper immersion, virtual and augmented reality experiences are revolutionizing space education. Strapping on a VR headset can transport you to the edge of an accretion disk, where you float beside superheated plasma spiraling into the abyss. You can reach out as the distorted stars of the galactic core whirl around you in a silent, cosmic ballet. Augmented reality apps can project a supermassive black hole onto your living room table, letting you walk around its event horizon and peer into the shadowy depths of its photon ring. This sensory experience builds an intuitive understanding that pages of text simply cannot, making the bizarre time dilation and one-way nature of the event horizon feel viscerally real. Educators consistently emphasize the power of this approach. As one planetarium director noted, the moment a student manipulates a virtual black hole and watches light bend, the concept shifts from a frightening mystery to a solvable puzzle. This active engagement helps you form your own mental model of the interior, whether you envision a cascading waterfall of space-time, a holographic screen of information, or a gateway to another universe. By engaging with these tools, you move beyond passive learning and become an active explorer. You can test the theories for yourself, fostering a personal connection to the greatest mysteries of the cosmos and empowering your own journey to visualize what lies beyond the point of no return. These cosmic gateways force us to question the very nature of reality. The existence of black holes represents what philosopher Thomas Kuhn called a paradigm shift, a fundamental rupture in our scientific worldview. For centuries, we believed in a predictable, causal universe where information is sacred and time flows in one direction. Black holes shatter these core assumptions, presenting us with a reality where information can seemingly vanish, time can freeze, and the laws of physics break down. This is not merely a new discovery, it is a challenge to our entire framework of understanding, forcing a profound scientific and philosophical revolution. The event horizon serves as a powerful metaphor for all human boundaries, the line between life and death, the known and the unknowable, the finite and the infinite. It echoes our own experiences of crossing personal points of no return, moments after which our previous reality is irrevocably altered. What does it mean for our concept of identity if all that defines an object is erased at a singularity, leaving only mass, spin, and charge? If our own universe was born from a black hole in a parent cosmos, what does that imply about causality and our place in a potentially infinite chain of being? Philosophers of science like David Deutsch argue that such ideas test the limits of empirical knowledge itself, pushing us to consider realities that are, by their very nature, beyond direct observation. The black hole becomes more than an astronomical object. It transforms into a mirror reflecting our deepest questions about meaning, mortality, and what lies beyond all perceived limits. This journey to the edge is ultimately a journey inward, compelling us to reconsider what is truly fundamental in a cosmos that can so easily erase the very things we believe to be permanent. Black holes have long escaped the confines of astrophysics to become powerful symbols in our collective imagination. Artists, filmmakers, and writers have repeatedly turned to this cosmic void as a canvas for our deepest fears and wildest hopes. In film, the monstrous gravity of a black hole often mirrors a psychological abyss. The movie Event Horizon uses a fictionalized version as a gateway to literal hell, a perfect machine for horror where the unknown becomes a source of pure dread. In stark contrast, Disney's earlier film The Black Hole framed it as a philosophical challenge, a mysterious boundary forcing its characters to confront their own morality and purpose. These stories reveal how a single scientific concept can be molded to explore terror, curiosity, or the very nature of the human soul. Beyond the screen, visual artists strive to make the invisible tangible. Painters use swirling vortices of color and distorted perspectives to evoke the warping of space-time, creating landscapes where light itself seems to bleed and curve. Composers have attempted to translate cosmic scale into sound, using vast, dissonant chords and deep, resonant frequencies to produce a feeling of immense, empty space and profound mystery. For these creators, a black hole is not a set of equations but a wellspring of emotion. We spoke with a digital artist who collaborates with astrophysicists. She explained that her work is a translation, taking data from simulations and rendering it into a form we can feel. Her pieces are not literal illustrations, but emotional interpretations of tidal forces, gravitational lensing, and the eerie silence beyond the event horizon. She aims to create a sense of awe that is both beautiful and terrifying, a visual echo of the science. This cultural resonance proves that black holes are more than astronomical objects. They are modern myths reflecting our timeless struggle with the unknown and our insatiable drive to find meaning or create it, even in the face of absolute oblivion. Our next window into this darkness is already opening, with a new generation of tools designed to probe the abyss. The James Webb Space Telescope, with its unparalleled infrared vision, is now studying the violent physics of accretion disks in exquisite detail. By analyzing the light from these swirling maelstroms, it can measure the spin of supermassive black holes and map the complex magnetic fields that channel matter toward the event horizon. Each observation provides a crucial clue about the chaotic environment just outside the point of no return. Soon, this effort will be joined by the space-based LISA mission, a revolutionary gravitational wave observatory. While current detectors like LIGO listen to the high-pitched chirps of stellar mass black holes colliding, LISA will sense the low-frequency rumble of supermassive black holes merging across the cosmos. These colossal events warp space-time itself, and their gravitational wave signals will carry an imprint of the black hole's final moments before merger, potentially revealing secrets about the nature of their event horizons and the mysterious interiors they conceal. On the ground, colossal instruments like the 30-meter telescope will use adaptive optics to peer into the heart of our galaxy, resolving details on a scale once thought impossible. It could see individual stars whipping around Sagittarius, a star with incredible precision, testing general relativity in the most extreme gravitational field we can observe, and perhaps even spotting flares from material as it crosses the horizon. The director of the Event Horizon Telescope project, Shepard Doleman, has spoken of the consortium's ambitious plans to add new telescopes across the globe and even in space. He notes that their goal is no longer just to take a picture, but to make a movie of a black hole, to watch how its shadow and the fiery ring around it change and evolve over time. This dynamic view could show us the turbulent flow of space itself being dragged around a spinning black hole. Beyond astronomy, quantum computers offer a completely different path to understanding. These machines, which harness the strange rules of the quantum world, might one day simulate the quantum gravity effects at a black hole's core with an accuracy far beyond today's supercomputers. We could run virtual experiments to see if information truly escapes during evaporation or if space-time is fundamentally pixelated. Each of these projects is a massive international collaboration, uniting scientists across continents in a shared quest to answer the same fundamental questions. The data they gather in the coming decade will not just provide more details, it will challenge our most basic assumptions, forcing us to rewrite our models of what happens in the ultimate dark. Black holes are not the cosmic vacuum cleaners of science fiction. This pervasive myth stems from a misunderstanding of their gravity. A black hole's pull is not some magical suction. It is governed by the same rules as any other massive object. Its gravity is finite and strongest at its center, weakening with distance just like the sun's. Many stars, in fact, orbit the supermassive black hole at our galaxy's core, Sagittarius a star, in stable, predictable paths, much like planets orbiting a star. They are not being devoured, they are dancing with the darkness, held in a gravitational embrace. A better analogy is to think of gravity not as a bottomless hole, but as a hill. Every object in space creates a dip in spacetime. A planet makes a shallow dent, a star a deeper well, and a black hole an incredibly deep, steep pit. If you are far from the pit, you can orbit it safely. Only if you venture too close to the edge do you slip in. They do not roam the galaxy, consuming everything in their path. They are more like gravitational anchors in the cosmic ocean. Another common fantasy involves time travel and stable wormholes. While the mathematics of general relativity allows for such structures, they are incredibly speculative. The kind of traversable wormhole you see in films would require exotic matter with negative energy to stay open, a substance we have never observed in meaningful quantities. Without it, any passage would collapse instantaneously, crushing anything inside. These are thrilling theoretical possibilities that push the boundaries of physics, but they are far from established realities. For those seeking to separate fact from fiction, resources from NASA and major observatories provide clear, accessible explanations grounded in real science. By letting go of these myths, we can appreciate the true wonder of black holes, not as simple monsters, but as complex engines that may have even helped shape the galaxies we see today, their intense gravity influencing the birth of stars and the structure of cosmic neighborhoods. The reality is far more strange and magnificent than the fantasy. This relentless quest to understand black holes is a profound testament to human curiosity itself. It is a story not just of physics, but of people who dared to ask questions that seemed absurd to their contemporaries. John Mitchell conceived of dark stars when the very nature of light was still debated, his idea a lonely beacon of thought. Subramanian Chandrasekhar faced public ridicule from the esteemed Arthur Eddington for his calculations on stellar collapse, yet he held fast to the mathematics, trusting the numbers over convention. Stephen Hawking revolutionized our view not by looking through a telescope, but by staring at equations, following them to the startling conclusion that black holes are not eternal. These pioneers were driven by a deep-seated need to know, to push past the boundaries of the accepted and explore the terrifying and beautiful unknown. Their journey was not a straight line to easy answers, but a winding path filled with doubt, debate, and moments of stunning clarity. This is the true engine of science and of human progress, the courage to ask a big question, even when you have no idea how to answer it, and the perseverance to keep searching when the answers seem impossibly distant. The value lies not only in the discoveries we make, but in the act of seeking itself. This pursuit reshapes our culture, fuels our art, and expands our collective imagination, reminding us that we are a species built to explore. So consider the mysteries that captivate you in your own life, the big questions about your work, your relationships, or your place in the world that feel just out of reach. Facing that personal unknown, that intellectual event horizon can be daunting, yet it is in that very act of questioning, of leaning into the mystery, that we often find our greatest growth. The story of the black hole teaches us that the most profound journeys begin not with answers, but with a single, courageous question asked in the dark. Your own perspective on this mystery is just as vital as any equation. We have journeyed through theories of singularities and wormholes, but the story is far from over, and it is one we are writing together. So I want to turn the question over to you. What do you truly believe happens beyond the event horizon? If you could design a perfect experiment to probe that darkness, what would it look like? Perhaps you imagine a fleet of quantum-entangled probes, where one falls in and its partner, light years away, instantly reveals a hidden signal. Or maybe you envision a future where we could stabilize a microscopic wormhole, just long enough to send a single photon through and see what, if anything, comes back. Some of you might have even wilder theories, like the idea of a black hole ecosystem, where the interior is not empty but teems with exotic forms of energy or even life, adapted to a reality where space-time has no meaning. Your thoughts and questions fuel this exploration. Share them in the comments below. Tell me your most plausible fate for matter or your most far-fetched cosmic blueprint. I will be reading through your ideas, and the most compelling ones could shape our future discussions, featured right here in upcoming videos. This is not a one-way lecture, it is a collaborative mission to map the unmappable. Your curiosity is the most powerful instrument we have. The quest to understand black holes carries a profound ethical weight, a responsibility that grows with every new discovery. Consider the theoretical possibility, however remote, of creating a microscopic black hole in a particle accelerator like the Large Hadron Collider. The laws of physics as we understand them suggest it would evaporate instantly due to Hawking radiation, posing no threat. But this very experiment forces a global conversation about the limits of our curiosity and the need for rigorous safety protocols that transcend national borders. The potential discovery of a traversable wormhole would present an even greater ethical dilemma. Such a gateway would be the most powerful technology imaginable, capable of reshaping travel, communication, and even the balance of power on Earth. Who would control it? How would we ensure its use benefits all of humanity and not just a select few? These are not questions for physicists alone, but for philosophers, policymakers, and every global citizen. This underscores the critical importance of international cooperation in fundamental research. Projects like the Event Horizon Telescope and the LISA Gravitational Wave Observatory are not owned by one nation. They are collective human endeavors. Scientists from competing countries work side by side, sharing data and insights because the mysteries of the cosmos belong to everyone. An ethicist who advises scientific organizations notes that the equitable sharing of cosmic knowledge is not just an ideal, it is a practical necessity for navigating the unknown safely. The insights gleaned from black holes could one day revolutionize our technology, perhaps leading to new energy sources or a deeper understanding of spacetime itself. Such power must be guided by wisdom and a long-term vision that prioritizes the stewardship of our planet and our species. Our journey to the edge of the unknown must be undertaken not only with brilliant minds but with thoughtful hearts, ensuring that our cosmic curiosity always serves a greater good. A star's death can lead to several different cosmic destinies. Compare the final stages of a star's life to the path of a single ball of clay. In one scenario, it is gently pressed into a dense, smooth sphere, a white dwarf. Apply more pressure and it is compressed into an even harder, smaller sphere, a neutron star. But push it beyond a critical limit and the clay collapses into a hole, vanishing from our reality entirely, leaving only its gravity behind. This is the fundamental difference between a black hole and its stellar cousins. A white dwarf, the remnant of a star like our Sun, is supported by the quantum pressure of its electrons pushing back against gravity. It is incredibly dense. A teaspoon of its material would weigh as much as an elephant here on Earth, but it still has a surface you could theoretically stand on. A neutron star is the next stage of collapse where protons and electrons are crushed together to form neutrons. It is so dense that a single sugar cube of its matter would outweigh Mount Everest, and it possesses a solid, unimaginably hard crust and a magnetic field trillions of times stronger than Earth. You can observe a neutron star often as a pulsar, its lighthouse beam of radiation sweeping across space. A black hole, however, offers no such surface. There is no crust to touch, no magnetic field to measure in the traditional sense. It is not an object but a region, a hole in space-time where gravity has won the final, absolute victory. The matter that formed it is gone, replaced by pure, warped geometry. This distinction becomes even clearer when we look at the most luminous objects in the universe, quasars. These are not black holes themselves, but the incredible light shows they power. A quasar is the frenetic accretion disk of a supermassive black hole in a distant galaxy, feeding on vast amounts of gas and dust. The energy released as this material spirals inward and heats up can outshine an entire galaxy of 100 billion stars. Yet the engine of this brilliance is the absolute darkness at its center. The quasar is the fireworks display, but the black hole is the silent, invisible cannon that launched them. The fate of matter in each case is starkly different. In a star, matter fuels nuclear fusion. In a white dwarf or neutron star, matter reaches a stable, if extreme, state. But in a black hole, matter crosses a threshold and simply ceases to exist as we know it, leaving behind only its mass, spin, and charge as a ghostly signature. This is why the black hole's interior remains the ultimate mystery. We can study the surfaces and magnetic fields of neutron stars. We can analyze the light from quasars. But beyond the event horizon, all such probes fail, leaving us with only the profound predictions of theory to guide us into the dark. The relentless pull of a black hole's gravity finds a strange parallel in the human drive for answers. Yet the most profound truth in science may be that some questions are meant to remain unanswered, at least for a time. This enduring mystery is not a failure of our intellect, but the very engine of discovery. Admitting we do not know something is the first, and perhaps most courageous, step toward a deeper understanding. It forces us to question our most basic assumptions, to tear down old models, and to build new ones from the ashes of our ignorance. This process is the heartbeat of scientific progress. Consider the humble star. For centuries, humanity gazed at the heavens with no true idea of what made the stars shine. The best theories suggested they were simply burning balls of coal, a concept that could not possibly account for their immense energy and longevity. It was a beautiful, frustrating mystery. That mystery drove the research that eventually revealed the true power source, nuclear fusion, locked within the atomic nucleus. The long path to that answer required the collaboration of physicists, chemists, and astronomers, proving that no single mind could solve the cosmos alone. The journey itself, filled with wrong turns and brilliant insights, was as important as the final destination. Our quest to see beyond the event horizon is no different. The paradoxes and puzzles we face today, the fiery debates over singularities and information loss, are the growing pains of a science on the verge of a revolution. They are signs that we are asking the right questions, pushing at the very boundaries of what is knowable. There is a unique beauty in standing before the unknown, a humbling awe that connects us to every curious person who ever looked up at a star-filled sky and wondered. So as we continue to build ever more powerful telescopes and run ever more complex simulations, we must also learn to cherish the questions themselves. The dark heart of a black hole may forever guard its secrets, but in our relentless, collaborative pursuit to uncover them, we discover something just as valuable: the limitless potential of our own curiosity. Our journey through the ultimate boundary has revealed a cosmos far stranger than we ever dreamed. We have ventured from the silent crossing of the event horizon to the shattering paradox of the singularity, a place where the very laws of physics dissolve. We have confronted the terrifying possibility of spaghettification and the hopeful vision of wormholes, cosmic tunnels that could connect distant stars or even birth new universes. These are not mere fantasies, but frontiers of human thought, where the destruction of information challenges quantum law and the holographic principle suggests reality itself might be a projection. Black holes are not cosmic dead ends. They are dynamic engines, potential gateways, and the ultimate classrooms for our most fundamental theories. This entire exploration stands as a testament to our boundless curiosity and the collaborative spirit of science, where mathematicians, physicists, and astronomers work together to illuminate the darkness. As Carl Sagan so beautifully reminded us, somewhere, something incredible is waiting to be known. The event horizon is one of those incredible somethings, a mystery that does not end our quest, but truly begins it, inviting us to keep questioning, imagining, and reaching for the stars. If you want to continue this journey of discovery with us, subscribe for more deep dives into the universe's greatest mysteries, and let us know in the comments, what do you believe is the most thrilling possibility for what lies beyond the point of no return? The conversation about our incredible cosmos is just getting started.